In this video, I'm going to walk you through some data and some methods for predicting stock returns that is fairly typical. So I start with this data set, and this is available to you. It's a little bit larger than data sets we've been using, but we can read it in, and it'll take a little bit longer than normal just because it's a larger data set and there are more variables and more rows in it. And we can do a summary of that data. First, let's look at the data itself. So PERMNO is the firm identifier, and this just comes from a different data set. That's why it's a different identifier. Date is the end of month date. So here this is January 31st of 1985. This size group is for different size stocks. So we have mid-size, and then we have large or big. I can't remember what the word for it is. Return adjusted is the end of month return. So the month from holding from the end of one month to the end of another month. So this return right here, this 16% return, is the return from holding this particular company's stock from December 31st of 1984 to January 31st of 1985. And it includes if you get dividends or delisting returns as well. INST, this is the percent of the stock that is held by institutional investors. So this particular company is held by 58%, or 58% of the stock is held by an institution or institutional investors. And then everything else here is something that is used to predict stock returns using a big list of variables that are out there that includes primarily accounting information, but then also some stock market information. And in the slides, I'll talk to you about what some of these mean. But it's a large number of variables, about 60. So see all of these things that predict stock returns, and I notice all the numbers look fairly similar. That's because I've already cleaned it up and standardized it in a way that we don't have to deal with missing values or outliers at this point. But if you were to create that data yourself, you would need to do that. So doing a summary of the variables, again, you notice they all have a maximum of 1, a minimum of 0, of negative 0.8, and the distribution is very similar across all of these, and we have lots of these variables. And then we have the dates go from 1985 to 2021, the end of 2021, and these returns on average for each month are fairly small, so the mean return is 1%, but the minimum was negative 174%, which is impossible. You can't lose more than 100% in a stock, and 160. What is 1600? So 16,000% return. So these returns have quite extreme values in there, and here these are even potentially some errors in the returns. So if we wanted to, we would go ahead and clean up some of these returns, but we don't have a basis for doing that, so we won't do that right now. And by the way, if you clean a lot of it up, nothing changes very much. Okay, then we're going to set up a training and a testing data set. So here I'm just going to start with 2005 like we've done before, but now we only have a date and not a year in here, so this is how you set up an R date. So the year dash month dash day. There are other ways to do it as well. And now we have two data sets. This splitting by time is also how it's often done when you're doing back testing, when you're creating trading strategies or testing trading strategies. And the reason for that is you want to create something in the past, create a model, predict returns, and then hypothetically you would go to the next period and try and trade on it and see how it does, update your models, do it again, and so you would keep repeating this. So for this reason, often when we create training data sets with return prediction sort of data, it's based on time in some way. To make some of the things easier, I've created here a data set that takes all of the training variables, so it only uses the y variable and then all of the possible x variables. I'm just doing that because it makes it easier in some of the things that follow. So I create a new data frame that is this training variables data frame, and I'll do another one later also. The reason to do that is now when I create this model, so this LM is a linear model, this is just the linear regression, the Y variable is this adjusted return, and the dot is everything else in that data frame. So I don't want to have the firm identifier and the date in there. Another thing to notice is this return is after all of these things that are available. So when we see leverage, this leverage is available before we start having this return. So let's go back to this data set. We'll look at the training one. So this leverage here is available before December 31st, 1984, so that we could hypothetically buy or sell the stock on December 31st, 1984, and hold that to see the return that we would get all through January of 1985. So all of this information over here is set up to be before the return that we get. Okay, so we run this, we get a model. A few things to note about that model. Notice the R-squared's low, and that is always the case with these return models, or at least when we're trying to predict individual stock returns. So you might say, oh, I should just give up. This is not even worth it. And if you're thinking about R-squareds, that's going to be the case. Of course, you can see there are some things that work. So some of these things predict stock returns. So for example, companies that have higher return on assets, so their accounting return, have a positive coefficient, meaning they have higher returns in the following month. So there are a lot of things in here that do work and seem to predict returns, but the amount of returns it predicts is really small. That's just because there's lots of noisy variation in returns. So you might say, well, why do we even try this? Why don't we just give up and not try and predict stock returns? Well, the main reason is because even if you can barely predict returns, that has the potential to earn you significant amounts of money. So I'm going to show you how this works. I will try and go slowly through how I set this up, but then you may have to work around with it and try different steps, individual steps here. So the first thing is to create a prediction from the model that we created. So here's the model. I'm just going to work with the training data set for now, because remember, we don't want to peek at the testing data set until we're comfortable with what we have. So we'll go to the testing data set later. So we create this prediction with the training data set, in other words, the fitted value. And I created a function here that is a trading strategy based on what you predict for a particular stock's return. So let's look at what that looks like in the training data set just to make sure we understand what's happening. So we go to the end here. You need this double one to get all the way to the end. So here's this prediction for this particular stock in this month. The prediction at the beginning of the month would be, this is your monthly return. Of course, it's really small, but this is your monthly return that's predicted. So then you can decide based on what you predicted what the strategy is going to be. So let me talk about this strategy. There are lots of different strategies that people use, and that's part of the way you try and make money is by your strategy. So this is as simple as I could think of in terms of coding. So what I first do is separate whether you predict a positive return from a negative return. So this is, you should have recognized all of this. I take the data set that I'm inputting, which is going to be this training data set, and based on that prediction that I just created here, I'm going to say if it's positive, then I'm going to treat those ones differently from the ones that are negative. So I just have this dummy variable that is equal to 1 if it's predicted to be positive and equal to 0 if it's not predicted to be positive. Then I group each month whether you predicted it to be positive or negative each month. Then this is the part that creates the trading strategy, and I weight the companies, all of the companies in the data set, by how their predicted value is relative to all of the other predictions. So you can work this out in a spreadsheet or something. So if these are negative, then this prediction is going to be negative. If it's positive, then the prediction is going to be positive. And we do the absolute value so that we don't mess up whether it's negative or positive here. So the denominator will always be positive. And this adds up how big the predictions are for the entire positive or negative part of the data set. So if we predict, let's say, 10% return for one company and 1% return for another company, and all you have are those two companies, then that would be an 11% total absolute return. So in other words, this is giving the percent, sort of how high in the predictions that you have does this particular company rank. And we're going to use that as the weight that we're going to put in the company when we make the investment. And so how you create a portfolio return is you take the weight that you have in that company, multiply it by the return that that company had, and then add all of those up. So if you had 50% of your portfolio in Walmart, and Walmart had a 20% return during this month, that would give you how much that return in Walmart affected your portfolio return. Let's say, to finish it out, you had 25% in Target and 25% in Lowe's. So then you would multiply 25% times each of those returns and then add all of those up. That gives you, it's a weighted average return of your entire portfolio. So then what this will give you is, for your positive positions, a portfolio return for each month, and for your negative positions, because we're grouped here, remember, for each month, the negative position portfolio. And notice if it's positive here, then this will be positive. When you multiply these together, let's say it actually turns out to be positive, and your weight is positive, then you're buying that stock and you made that money. When it's negative, this will be a negative return because you predicted it to be negative. Let's say it does turn out to be negative, so this is negative here, the weight is negative here, those together will go to be positive, so then that will be a positive return. Well, why that works is because a negative weight happens if you go the opposite direction from buying. So if you sell the stock, or there's a term called short selling, if you short sell the stock, then you get the opposite of the return that is there that you would see in the stock market. So if the stock price went down 100% and your weight was negative, meaning you shorted that stock, you would get the 100% positive return by shorting that stock. Then I group by date, so now I just want to put those positive ones and negative ones together, and so I just sum up those two returns so that I have only one side now. So I have, what this is doing is saying I'm taking 100% going long in the positive side and 100% going short in the negative side. So then this creates a monthly portfolio return that I would have earned if I had used this particular strategy. And of course, if I actually predicted what turned out to be the case. So the training data set will always give you something that is way better than you could actually get, because this isn't, you're looking back in the data, not trying to predict. Then I have a couple of outputs that help us to evaluate in a way that's different from an R-squared value how well how my portfolio performed. So this is the mean of that monthly portfolio return. often we report those in annualized measures. It's not always perfect, but the basic idea. So I multiply this average portfolio return times 12. This gives me an approximate value for the annual return. And to annualize the standard deviation, I have to multiply by the square root of 12. So same thing here, I take the standard deviation of the monthly return, multiply by the square root of 12. Then there's something called a Sharpe ratio, which compares the mean to the standard deviation. That's what investors, or that's one measure that tells what investors care about, because they want higher average returns but lower risk. So if you can lower the standard deviation, meaning the portfolio return doesn't bounce around a lot, and the mean is higher, then they like that better, or at least that's the idea. So then here I'm doing something different. I'm going to output a list of all of these pieces. So I'm going to output the mean, the standard deviation, the Sharpe ratio, and this port data set here that I created. And because it's going into a list, that's going to create it's going to create a list from the first part of the column, which is the date, and the second column, which is the portfolio return. All right, so this is my function that I created. It's a little bit long, and I like it because it simplifies doing this, but you could do this each time, and you could figure this out piece by piece if you wanted to. Okay, so I run this portfolio evaluation. Notice I already predicted for that predicted return, and I save that as this test1 data frame, and you can look and see what happened with, so test1, to look at a part of a list, you can do these square brackets. So test1 square brackets gives me the first object here in the list. So the first one is the mean. So the mean return, annualized return, would be 42%. The standard deviation, annualized standard deviation, would be 13%. And the Sharpe ratio would be 3.15. So anecdotally, what I've been told is if you can get a Sharpe ratio above 3, then you've got a money-making strategy that you could go sell to people, or somewhere around that anyways. Of course, this is false backtesting, so we would never tell someone that we can do something like that right here. Then for 4, I'm just going to do a summary so it doesn't output all of it. Notice it gives me the dates for the data frame. It went from 1985 to 2004. That's because this is the training data. And the portfolio returns that I get out of that, well, the mean was 3%. So that's the mean monthly return. So if you multiply that by 12, then you would get this 42% annualized return. We had one month where there was a 25% return on the portfolio and another month where we lost 15% on the portfolio. That sounds kind of scary and risky if you're going to do that type of investment. Okay, so that's how we're going to think about evaluating the returns, or the strategy and the model. That's important because the 1% R squared translated into something, this 40% average annualized return. If you actually could achieve that, that would be fantastic. You would be super wealthy, and I'll show you some of that in a little bit. So the 1% is significant when you go to start developing these trading strategies. Okay, so the R squared doesn't translate directly into something that you can think about portfolio-wise. Okay, I want to introduce another thing. So what about when you have lots and lots of variables? How do you decide which of those variables to put in? And this is related to one of the questions that came up before. What should I put in my model? Well, what has happened over the years is people collect more and more things that you can put in these return models, and hypothetically you could collect everything possible that anyone has ever said that will predict returns and put it in your model. Of course, that starts to become cumbersome and can take a long time to create all of this data and collect it and get it ready. And it may or may not help. So one of the things that happens often is trying to select from the variables which ones of those you should use. Okay, so I'm just going to show you how to do this. There are lots of ways to do this. You can look at those and look them up in R. You can do a stepwise selection. There are problems with that. Of course, people do it all the time and it works fairly quickly. You can just look at those and say, oh, it's not significant, so I'm just going to keep certain ones in my model. Again, that can work. Or like the variable importance that we've looked at, just keep, you know, the most important variables. All of those things are things you could do and may help or not. I'm going to introduce one that is called the recursive feature elimination. And there are a number of possibilities. This one goes through the Caret package. That's why I like it, because it's something we've been working with. And I'm just going to do the linear model version. So notice here I have return adjusted and then everything else again. And this just will do the linear model. And how it knows is this part up here. So I'll talk about this in just a second. But the benefit of this is what it does is just like when it's doing this cross-validation that we've done for training a model, it will take out a variable, check it on the data, and then try and take out another variable, and it will keep going through this and repeating it, trying to find a model that performs just as well, but even when we reduce, you know, we cut out some of those variables. So I ran this. By the way, this takes a little while, so you might want to save up some time for it. Let me highlight just a couple of things that are different. So this RFE control, this is the recursive feature elimination control. So that's different from what we had before. We had a train control thing here. And the functions you have to tell it is the certain type of model. So we're just going to do this linear model function. And then after you see it, it's great to have in your toolkit, but then you might just be a little depressed with what we see anyway. So, and then the rest is stuff we've already seen: repeated cross-validation, repeat it 5 times. Verbose equals false means don't output stuff while it's running. And so then the function is RFE, so that's the thing that says instead of train, it's going to run through the different variables and try and do a selection on that. Okay, so it runs through all of that. Then here you can pull out of that what it selected. So this is, I saved this object. This is like the model object we've created in the past. And best subset says which one of the models did it stick with. It said it stuck with, after trying a bunch of them, it stuck with all 60 variables being in there. So in other words, it couldn't, at least on this training data going back and forth and doing cross-validation, it couldn't find a subset that did really well. So we can look at the model output itself, and it tells us a little information here. So if we look at the R-squared, because that's something we've been looking at, when it used 4 variables, so it tried to find the best 4 variables, it would get 0.6% R-squared, tried the best 8, 0.8% R-squared, tried the best 16, 1% R-squared, tried the best 60, 1.1% R-squared. So notice it didn't go up as much, you know, once we went from 16 to 60. So it got most of the way there with 16, but it still thinks it's better, and we could adjust how we tell it it's better or not, but it still thinks the best thing to do is just include all 60. So all of that variable selection, and we didn't get very far. And that doesn't always have to be the case. In a lot of data, you may see that it actually works to include a smaller subset. Or if we mess around with how much we require it to improve or things like that, we could do that. But one of the outputs here, it says the top 5 were these variables. So we could try that and see what happens. So that's not the same as doing a great variable selection that's robust, but it says we tried all of these things and these are the ones that seem to matter the most. So we could create another model that just uses this subset. So I'm going to do the same thing. So estimate the model, predict for the training data set. So now the predict is for my second model, not the first model, so I have to be careful with that. And then I'm going to create this test 2, which is evaluating the portfolio based on this prediction here. So test 2, the first object is the mean. Notice I have a 36% annualized return. Before it was 40-something%. So it's gone down a little bit, but not a whole lot. It's a little worse, but not too much worse. Then the standard deviation, about the same. The Sharpe ratio went down a little bit. So by looking at only these 5, it went down a little, not a whole lot, but it went down some, okay? Well, there's another way we can look at this to try and figure out over time, would this start to matter? And that's called a cumulative return. So in other words, if you invested $1 at the beginning of the sample and held it until the end of the sample, what would your return be? And let me walk through that just a little bit. So in here we have this test 1, the 5th part of the list are the returns, the portfolio returns. So I'll show you that here. So these are the monthly portfolio returns. And we need the double square brackets because it pulls it out and lets us work with those numbers. So otherwise it labels it sort of, and so we can't directly access the numbers that way. And how you know is you try it with single square and double square. At least that's how I do it. And if it doesn't work, oh, I better go look at it again. So we're going to do the cumulative product. And so how that works is we say each month, if you start with the dollar you started with, you add the return that you just got from during that month, and then that's what you start with the next time. And so how you accumulate those returns is multiplying 1 plus that, as you work your way down every month. And then at the end, subtract 1, that'll assume that you start at 0. That's sort of makes it easier to look at. So you can look up cumulative returns and how to calculate them. That's all over the place online. So then in order to graph it so you can see that, I'm creating it for the first model and the second model. And then I'm going to create a data frame that gives me the date and these cumulative returns. So I run this. And by the way, I didn't set the seed, so you may get just slightly different results than I do. So we look at this, of course, remember this is in sample. Notice it started at 0. So that's because we subtracted this 1 at the end. If we didn't subtract this 1, then it would start at $1. So if we started at 0 and held it from 1985 to 2005, we would have more than a 3,000% return, like a 3,500% return. For using all of the variables, and we'd have 1,000% return just from using the smaller set of variables. So quite a big difference in terms of what we would hypothetically earn if we knew all of this stuff and things like that. So pretty big difference as we get further along. So if the training data actually is what happens, then we would want to make sure to use the full model with all of the variables. So now the big test is, let's move to out of sample. So let's go to the testing data set, and we're just going to repeat the stuff we already did. So take the model that we estimated on the training data, apply it to the testing data set, and save this prediction in the testing data, and create a portfolio out of that. And so I'm just doing test 1, and then I'm adding this TST to make sure I remember it's the testing data. And we can look and see what happens. So the mean return was 24%. Well, not bad, right? It's less than the 40%, so we lost quite a bit. So it doesn't perform as well out of the training data, which of course we would expect. And the Sharpe ratio is 2.8. Still pretty good, but not as good as in the training data. So remember I said the 3.0 cutoff, so then it's borderline. Like, should we think about pursuing it? it's not so high that people would be like, oh yes, let's go do this, but it's at least marginally close. Then we can do the same thing with the smaller model, and we see 20 averages, rounded to 24%. Well, that's basically the same as what we get using all of the variables. So what has happened, and you'll see that when we do the cumulative returns, and here's the Sharpe ratio, 1.7. Now that's quite a bit lower. But what has happened on the average returns is what was a big difference over here in the training data set became less of a big difference. Of course, the Sharpe ratio has gone down with the smaller model. That means the standard deviation, the volatility of the portfolio has gone up. Okay, so then we do the cumulative thing, exactly the same as before, just change things to the testing data set. And what has happened? Well, now we still have too high of a return, right? Now it would still be over that entire period, you would still have a 40% cumulative return, or a 50% cumulative return. So that's pretty good. But now the two models are very similar. So including all of the variables seems to have smoothed out the model a little bit. So notice the blue one is bouncing around more than the black one. So reducing the set of variables increases the volatility of our portfolio, but on average it looks sort of similar. So notice we sort of end up in a similar position as if we were to hold that whole period. So there are these trade-offs that you have to make when you're thinking about these models. It's not always straightforward to say we should look at all of the variables or we should look at a smaller set of variables, and depending on the research question or what you're interested in, you may come up with a different answer. But importantly here, I think what we see is we perform better with all of the variables. We can't seem to find a good subset that performs better. There are some research papers out there that try and come up with different variable selection models that maybe perform a little bit better than not doing those selection models, but there's so much variation in the results that my guess is that's not consistently something you can rely on. Okay, so what I'm going to have you do in the homework is mess around with some of this, try some different things. Really, I just want you to get a sense of what we're trying to do and the types of models and things that we work with when we're dealing with stock returns. This isn't the only approach that people use. There are lots of different ways to approach trading strategies and using this accounting information to predict returns, but this is fairly standard. A couple of warnings, things to note, right? You say, oh wow, this trading strategy looks good. Well, there's a lot of evidence out there that we couldn't actually go trade this and make money. So these are just paper profits. They look good, but when you go to trade them, they don't perform as well in real life. So part of the homework will look at some of that to get a sense of that, but it's also what gets people excited of maybe they can figure it out better than someone else could figure it out. And then in the next week, we're going to talk about selecting different models with the same data, which hopefully will give us some different insights as well.